Hello, this time we're going to be looking at the counterpart of exponential functions, and you're going to learn a new type of function called logarithmic functions, which take a little bit of getting used to, quite frankly. In mathematics, we like to be able to undo what we have been doing. For instance, when you were a child and you first learned to add, then you began to learn to subtract, which undoes addition. And once you learn to multiply, then division is learned to undo multiplication. These are called inverse operations. Well, we've learned some things about inverse functions in previous lessons. And those three qualities of inverse functions that we will be looking at over the next few lessons are, first of all, if f and f inverse are inverses of each other, then their compositions will equal x. In other words, f of f inverse of x equals f inverse of f of x equals x. Or a more simple way to look at this is, if I have point xy on function f, then its counterpart x comma y, or y comma x, will be on f of x, f inverse of x. And finally, the graphs of f and f inverse are symmetric to the line y equals x. Now, how does that apply with exponential functions? Well, logarithmic functions are defined, and this is an important point. They're defined to be the inverses of exponential functions. Hence, we get the definition that's in this bold print. Y equals the log base b of x if and only if x equals b to the y, where b is greater than 0. Remember, in exponential functions, our base had to be greater than 0. Hence, the same thing will be true in logarithmic functions as well. And again, we read this expression, y equals the log base b of x. Notice that essentially what logarithmic functions are designed to do are to switch x and y in the exponential function. Instead of having y equals b to the x, which would be our exponential function, in a logarithmic function, x equals b to the y. But instead of writing it that way, mathematicians have written it y equals the log base b of x. So let's see how that works out in some practice problems. We want to, in these first three problems, transform each of these logarithmic expressions into exponential expressions. So y equals the log base 4 of 16 will be equivalent to saying that 4 to the y power, 4 to the y equals 16. Or if we have 8 equals the log base 3 of x, that's equivalent to saying that 3 to the 8th power is equal to the number that we're looking for, x. Or if I have 2 equals the log base b of 25, that will be equivalent to taking our base b, raising it to 2, and that will equal 25. Now, just as we can transform from a logarithmic to an exponential counterpart, we can take an exponential expression and change it into a logarithmic expression. And so in these next two examples, we're going to be taking an exponential expression and looking at its counterpart. As you look on the screen, 3 to the x equals 81 is equivalent to saying that we have 81, the log base 3 of 81 is equal to our x. Or if we have b to the 5th equals 32, That's the same thing as saying our log base b of 32 is equal to 5. So you can practice some of these in your homework problems as well. Now, let's look at how we can apply the definition of the logarithmic expressions to find some numbers that involve logs. Let's let f of x equal the log base 2 of x. And as with other functions, we would be interested in finding what happens if we let x equal 1. We'll be looking at f of 1. And what happens if we let f of x equal 4 and f of x equal 0.25? Well, let's look at the first one of these, f of 1. Using our definition, remember that y equals log base 2 of 1, where x is 1, means that 2 to the y power equals 1. Now, as you look at 2 to the y power equals 1, we think 2 to what power is equal to 1? And hopefully we remember that 2 to the 0 power is 1. Therefore, the log base 2 of 1 must be 0. So, f of 1 is equal to 0. Or, said another way, the log base 2 of 1 is 0. Now, let's look at the other two. Since you have y equals the log base 2 of 4, for f of 4, in this case, that means 2 to the y is 4. But if you recall, 2 squared is equal to 4. Therefore, the log base 2 of 4 is 2. Or in our function, f of 2 up here will be, f of 4, will be equal to 2. And finally, if we take y equals the log base 2 of 0.25, that means that 2 to the y equals 0.25. But since 2 to the negative 2 equals 0.25, the log base 2 of 0.25 equals negative 2, or f of 0.25 equals negative 2. Now let's try practicing some of these without using a calculator, because frankly we do not have a log base 3 or a log base 5 on our calculators. We're going to be looking at how to solve that problem in a few minutes. But y equals the log base 3 of 9. We need to change that from that rather strange looking expression to something that most of us better understand, the exponential form, which will be our base 3 to the y equals 9. And we ask ourselves, 3 to what power is equal to 9? And in this case, we picked a very fortunate number because 3 squared is equal to 9. So we would say that the log y equals the log base 3 of 9 is our exponent, 2. What about the log base 3 of 1/9? Well, that means as an exponential view, 3 to the y equals 1 over 9. But we just found out that 9 is 3 squared, so that means it equals 1 over 3 squared. But we want that 3 to be our base in our numerator, and using laws of exponents, that becomes 3 to the negative 2. So y must be equal then to negative 2. So y equals the log base 3 of 1/9 must be negative 2. And finally, we're looking at y equals the log base 5 of 125. In its exponential equivalent, our base is 5 to the y value equals 125. And hopefully you recall that 5 cubed equals 125. Therefore, y must be 3. So y equals the log base 5 of 125 is y equals 3. We've looked at several examples. You're going to have several of these in the homework that you will be asked to do without a calculator. Why don't you go practice on those?